In this fourth and final video for SLO8, we'll be looking at some reactions of carbohydrates. And as the title of this section of our video suggests, the anomeric position has a special place in the reactivity of these kinds of structures. So to get started looking at this, we can consider a reaction of a cyclic form of a carbohydrate. So this is a pyranose, a 6-membered ring. And it turns out that this is glucose, and it's the alpha anomer of glucopyranose. So this is alpha D glucopyranose, and that's going to be the most specific name we can give this compound. If we actually maybe dissolve this sugar in methanol and added a little bit of an acid catalyst, maybe a couple of drops of HCl or sulfuric acid, and we would want to try to predict what might happen. And in the course of doing this and thinking about this problem mechanistically, I think the hope will be that we essentially discover why the anomeric position is where the magic is. So to get started, we would think about this process probably involving a protonation. It looks like conditions we've seen before for the formation of acetals, as well as some other kinds of reactions. So we know that those processes all involve protonation as an initial step. And if I look at where on the carbohydrate structure I could protonate, I'm seeing a bunch of different options. Alcohol, 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 alcohol. Any of those oxygens are going to be about as basic. So you could imagine a situation where the proton is basically playing duck, duck, goose with each of these alcohols. Like sometimes the proton's on this alcohol here on carbon 1 or the anomeric position. Sometimes it's on the alcohol of carbon 2. Sometimes it's on carbon 3. You get the idea. It could also protonate the ether oxygen, which turns out to be about as basic as the alcohols, roughly. It's not exactly equal to, but it's very similar, because this oxygen of the ether has very similar amount of electron density and electron stabilization as the other oxygens in their lone pairs. So it might be helpful for us to consider a couple of different protonated forms of the sugar. Because we know that each of them is accessible, it might be the case that only one of them gives rise to a reaction. So if we add a proton to, let's say, let's choose the alcohol at C3, so here on the left, we would end up with a structure that looks very similar. So we still have a pyran, we still have a bunch of OH groups, no stereochemistry has changed, but there will be a new oxygen that's positively charged, so that's new. And that's really what the protonation's about, what it does for us. So this is one possibility, one structure that we can form. And then let's also consider what happens if we protonate the alcohol of our anomeric position, so the C1 alcohol. So our structure, again, will be very similar, except for now our positively charged oxygen will be at C1. And let me put in all my other alcohol groups. So many functional groups. Okay, perfect. And we know that if this structure is in equilibrium with this one, and this is in equilibrium with this, then it's also true that these are in equilibrium with one another. So again, this is kind of illustrating this duck, duck, goose aspect of the proton can get onto each of these oxygens, but maybe only one of them gives rise to reactivity. So we'll see. Normally when we see situations like this, where we have a protonated alcohol, we think about having made a better leaving group. We've encountered this idea numerous times over the semester, and it's no different here. Carbohydrates are organic molecules. They have the same kinds of structures and reactivities that we might expect from other kinds of structures we've seen before. So here's our better leaving group. And our other structure we're analyzing, we have the same idea. We've made the alcohol at carbon 1, or the anomeric position, a better leaving group. And so one of the things that we could do is consider, well, this is a good leaving group. Methanol would probably be our nucleophile, and specifically the oxygen of our methanol. But I have to decide, will that oxygen actually displace directly this OH, or this water group, via basically an SN2 reaction, or will it more likely go through an SN1? And so to decide that, we need to consider a couple of things. One is how easy it is for the nucleophile to get in here. And the other is how stable the carbocation would be. So if I'm trying to decide what's happening here, I probably should at least draw carbocations, right? Maybe I can find one that's really highly stabilized, and that would give me a hint that probably any kind of a reaction would funnel through that intermediate. So I'm going to consider the case where my water structure is actually left. So I'm proposing a step like that. I don't know if it's happening yet, I'm just thinking through. So I'm going to draw the structure that would form if this water group were allowed to leave. Still have a lot of alcohol groups. You're going to watch some exciting video footage of me drawing OH a lot. And it looks like my carbocation will be here. Okay. Again, we're comparing two different sites of protonation. So if we want to do this comparison in a systematic way, and we do because we're students of science, we would consider the same possibility for our other protonated form of the alcohol. So rather than, and here we would basically dissociate water from carbon 1, or from the anomeric position. So, okay, lots of drawing to do. Plus OH, 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 okay. And in both of these cases, we've got a water molecule that's forming, so that's where the leaving group went. Should have drawn that in green, didn't draw it in green. Going to circle it in green just so you can correlate the leaving group and the water molecule since these structures are really complicated. So what's left for us to do is to analyze the stability of these two carbocations, right? Maybe one of them is more stable than the other. And if we find that one carbocation is more stable than the other, we know that it's far more likely to form than the other. So to do this, what I'd like for you to do is, well, you probably can guess, I'm going to ask you to analyze this carbocation. What types of ideas would you use to know how stable a carbocation is, and then apply those ideas. And then the same thing here, right? So in essence, which of these two carbocations is more stable and why? So pause your video and answer the question. So you've had a chance to think this through. And one of the things that you probably learned early on in your encounter with carbocations is that you want to think about the degree of substitution. So you might have learned something like primary carbocations are less stable than secondary, and secondary carbocations are less stable than tertiary. So you might think about things like tertiary carbocations as being stable. One thing I want to add here is that no carbocations are stable. These are all unstable intermediates. But stability isn't a yes or a no kind of a question. It's not a light switch like this. It's a dimmer knob like this, which you can barely see because it's a sunny day in Portland, which is a little surprising. So we see that we've got a secondary carbocation. And if I look at this carbocation, it's also secondary. So that can't explain any stability differences, and there may not be any, but it's not enough just to look at substitution patterns. As we've seen all semester long, groups that are adjacent to charges or lone pairs can make a big difference. This could happen by hyperconjugation or induction or resonance. We have to actually assess the local environment about charges and electrons. And so to do that, I could look at like this carbon is bonded to a carbon and another carbon. So really the best bet I would have is I would have hyperconjugative donation from this carbon here and this carbon here. But that's really what this secondary concept captures, right? It's counting the number of hyperconjugative donors. Okay, and that's going to be true here to some extent. But one of the differences that we see with this carbocation on the anomeric position is that there's an oxygen directly attached to this carbon. And we know from our conversation about carbonyls that oxygens have the capacity to be both inductive withdrawers of electron density, which should destabilize this carbocation, but they can also be resonance donors of electron density, which should stabilize the carbocation. So basically what we're invoking is this kind of a distribution of electrons from oxygen into a new OC double bond, and that's going to delocalize the positive charge. So now there's no individual atom that's bearing the brunt of a positive charge, and moreover, in the resonance structure we could draw for this kind of a carbocation, none of the atoms will have open octets. So I'm going to draw the resonance structure now. It's going to look a little more weird. One lone pair left on oxygen, positive charge on oxygen, double bonds, which I'm not drawing very well. Yeah, like that. Cool. So we can see that there's resonance stabilization for this carbocation in addition to this kind of notion of substitution, like secondary. So secondary plus resonance donation. So on the basis of these types of structural analyses, we could predict that this carbocation, the one at the anomeric position, is more stable than one of a carbocation elsewhere on our pyrran ring. And that turns out to be true for any of the other positions of the sugar. You could convince yourself of this by using the same kind of analysis. You could protonate the C2 alcohol, and you'd find you would just have like a normal-looking secondary carbocation. C3 gives it, that's what we analyzed. C4 would give you the exact same result. And then actually protonating the alcohol on C6 will give you a primary carbocation. So that'd be like even worse. So what we're seeing here is under acidic conditions, we essentially activate the anomeric position by making a very easily formed and relatively stable carbocation. So one of the things we want to take away from this discussion is that whenever you see the presence of an acid catalyst, you almost know when you're dealing with carbohydrates which site will be electrophilic. So this will activate the anomeric position as an electrophile, and it'll do it selectively. There's such a big difference in stabilization between this carbocation and any of the other options that this is going to form way faster than any of the other things that you could form. Okay. So we now know that our electrophilic site is the anomeric carbon because we're specifically making this alcohol a good leaving group, the anomeric alcohol. And so what's left for me to do is to make a prediction about what would happen if this electrophilic site bonded with this nucleophilic site, the methanol oxygen. So I know that most of the rest of this carbohydrate is going to stay exactly the same. So you get to watch me write more chairs and more OH groups. I know it's extremely exciting. And maybe you could fast forward the video and it'll sound like Alvin the Chipmunk, which I do when I edit these things, and it always makes me laugh. So I know I'm bonding the nucleophilic oxygen. That oxygen is going to be bonded to a methyl group still. I'm just using a lone pair from the oxygen. And that proton is still going to be attached. So initially I'm going to form a structure that looks like this. And I know that if this reaction is acid catalyzed, this proton will dissociate. So the final product, which you might actually expect to isolate, will be a structure that looks like this. So we've just lost the proton. I'm going to put my lone pair back on oxygen so you'd have a neutral species. But there's a couple of things I also want to point out here. One is that this is one of two products. So this carbocation here, positive charge on carbon, even though it's hard to see in these chair drawings, that carbon is trigonal planar, it's flat, like a piece of paper. And that means that the incoming nucleophile methanol can add from the top or the bottom in about equal amounts, which means that I'm going to form both anomers of my product. So this is one of my anomers of the product, and then you would also get the other possible anomer of this compound. Which brings us to our kind of second important idea, aside from acid catalysts are activating the anomeric position, is that the substitution reactions at the anomeric position will typically yield a mixture of anomeric products. Right, because if you look at the mechanism here, what we're basically proposing is an SN1, and we know that SN1s make racemic products. Well, racemic suggests that you make two different enantiomers, but that always is assumed, since you first learned about SN1 reactions, that there's only one stereogenic center. That's not true here. We've got a lot of them in these carbohydrate structures. So we're actually just basically making a mess out of one of those centers, but that centers the anomeric position. So we basically say that we make anomeric products. The logic is exactly the same as when you learned about racemization in the SN1. I also want to point out if anyone actually makes a really bad life choice and becomes a carbohydrate chemist, so not someone who deals with these in a biochemical way, but like synthesizes complex carbohydrates from sugar, basically, like, well, that's not right, from like glucose. This is a horrible thing to do. The NMRs look just awful. You can do SN2 reactions on certain kinds of derivatives of carbohydrates. And so in those cases, the same idea would apply, where you would end up forming essentially an inversion product. So this is not universally true. It requires you to proceed through a carbocation intermediate a la SN1 type chemistry. So in the next section of this video, we'll look at these kinds of what are called carbohydrate derivatives, to give them some names, look at some more suffixes and prefixes that we use to describe them, and look at some other examples. So it turns out that carbohydrate derivatives are actually some of the more important compounds that get used biochemically, and we also use some of them in consumer products as well. So I thought what we could do is take a kind of a sneak peek at a few types of structures that you may see in food chemistry classes or biochemistry classes, and we'll also talk in more detail about this type of a structure here, which is very similar to what we made in the last section of the video. So just for continuity's sake, we'll start with this thing that looks maybe a little bit more familiar to us. And we know that what we did was we substituted an OH group for some kind of an alkoxy group. In the previous section, it was a methoxy group. In this section, it's an ethoxy group. But we did this at the anomeric carbon. So this group we formed via anomeric substitution. And you can introduce a lot of nucleophiles to this position, right? We could put in alkoxy groups, you could do amines, cyanide, for instance. All of these things work, and they're all called anomeric substitutions because they're exactly that. You're replacing an OH group for something else. So one of the things I want to point out in these structures is that it looks like what we've done is made an acetal, which kind of makes sense because that's like the same set of conditions that we used when we made acetals from aldehydes or hemiacetals, some kind of an alcohol and an acid catalyst, right? We're just doing it on a more complex structure, so this is a direct application of what you saw in SLO7. I also want to point out something about the naming for these kinds of structures where we've done some anomeric substitution, and specifically for ones where we've actually introduced an ether group at the anomeric position. So this structure would be called ethyl, because we're introducing an ethyl ether of this group. D, so this is the D-diastereomer, enantiomer of this particular derivative. Alpha glucopyranoside. Okay, so this is kind of a mouthful, ethyl D-alpha glucopyranoside. Say that 10 times fast and your parents are going to think you're learning a hell of a lot in this class. But let's look at each of the pieces of these words to derive information. So the ethyl we talked about, it's a little bit self-explanatory. It corresponds to the group that you have at the anomeric position. If we'd introduced an isopropyl group instead, this would be called isopropyl D-alpha. You get the idea. We've still got gluco. So we're telling ourselves about stereochemistry at C2 through C5. Pyrano is still telling us that there's a six-membered ring. And this side suffix corresponds to the notion that we're making one of these acetal derivatives. So you can see that with sugar nomenclature, really you're combining lots of suffixes and prefixes, and we've seen this in other videos as well, but this is another place where it shows up. So you don't need to memorize any of these things. What's important to me is that you know to look at individual pieces of these, what seem like extremely complicated names, because each of them carries specific pieces of information that you can use. So the other thing that I wanted to point out here is this concept of what a derivative means, which maybe I should have started this section with. But the idea is that we are making these structures from the carbohydrates themselves. So if you actually counted all your carbons and hydrogens and oxygens for this kind of a structure, like you wouldn't end up with the carbohydrate pattern. You wouldn't end up with CN, H2N, ON. You'd have, too many hydrogens. I think you'd have too many carbons as well because you've got this ethyl chain, but it came from a carbohydrate. So we're trying to differentiate like a true carbohydrate from structures that look a lot like them, have a lot of the same stereochemical and functional group aspects, but are not like actual carbohydrates. Okay? So this compound here has a very different kind of a name. This is going to be D-alpha glucuronic acid. So again, if we look at this name, there should be some parts that we recognize, right? We have alpha, that's going to be our anomeric substitution pattern, right? So this oxygen group is trans to this carboxylic acid group, which is what we mean when we say alpha. Glucose, so we still have the same C2 through C5 stereochemistry, and then this ronic acid is telling me that rather than a bunch of OH groups, I have a carboxylic acid present. In this case, at the C6 carbon. So the reason I wanted to show you this isn't because I need to like have you memorize the structure or anything, but like this compound turns out to be in our bodies in large quantities. And this compound also is very highly associated with how we metabolize structures that we eat or consume in other ways. So if you imagine taking maybe some kind of an allergy medication, or it's been in the news a lot, like hydroxychloroquine, so it's one of the experimental COVID treatments, those compounds get metabolized. And the way that they do that is that there are various reactions that happen in your body, both in your liver and your gut, as well as other places, that try to make these structures more water soluble. And the idea is basically that as the structure becomes more and more water soluble, that they'll be able to dissolve into the water in your tissue, eventually pass through the kidneys, and you'll be able to pee them out. So they get them out of your body. That's what we really mean by metabolism in a way. So if we think about it, we know something about carboxylic acids. It's easy to make bonds to this carbon, right? We've actually activated this carbon as a place where we can substitute. And so there's a variety of enzymes that glucuronidate things. They basically add this whole unit via amides or ester bonds or whatever else you might have here. So you have this whole 6-membered ring, this pyran ring, that's basically sticking out off of the molecule, and it has all these OH groups, which is going to make the structure much more water soluble. Remember, likes dissolve likes. Well, all these alcohol groups look a lot like water molecules. And so when compounds get glucuronidated in your body, they're basically marked for clearing through your kidneys and out through your urine. So this is a really important metabolic pathway and something that medicinal chemists care a lot about. We actually look for places in molecules that can undergo these glucuronidation reactions and try to actually alter their structures so that that process is slower. And that allows the drug to exist in your body for longer, which helps you take less of that drug. Maybe you want to take a pill once a day, and at the end of the day gives you like a better drug. Okay, so 2 other substances I wanted to talk about. This one here is D-beta glucosamine. So you may have taken this, your parents may have taken this, your dog may have taken this. Glucosamine is one of these substances that's kind of supposed to be this miracle cure for joint pain and things like that. I don't know whether it works or not. I'm not going to take a stand there. But again, we can see this idea that we have information embedded within the name that now you understand how to interpret. Gluco, that's telling you about the C2 through C5 stereochemistry. Amine is, well, that thing. And so it's not necessarily obvious to me how we would make this as chemists, although we can. I don't want to go into that with you. This compound exists because it's essentially a direct substitution of an OH group for an NH2 group on a glucose molecule. So it is a sugar derivative, even though it has a nitrogen, which is like not even a part of our pattern of molecular formulas for carbohydrates. And then this final compound, well, this doesn't look like a sugar at all. First of all, it's acyclic, right? We don't have a pyranose or a furanose or anything like that. But this is a compound that you've likely consumed. This is xylitol. So this is usually the sweetener that's in sugar-free gum. So this compound actually comes from a carbohydrate that's been reduced. Sometimes we call these a reduced sugar. And if we look at the oxidation level of all of the carbons, it'll be clear why we call it that. So this carbon is +1, this carbon's +1, this carbon's +1, this carbon's +1, this carbon's +1. Wait, I thought I was supposed to have a +2 somewhere. Oh, right, because I've reduced a carbohydrate. That carbon that was at the +2 oxidation level is now at the +1 level. So these compounds are interesting because a lot of the metabolism that happens to sugars themselves, so not the glucuronic acids, happens at, or by reactions at the magic center, at the anomeric position, which is at which oxidation level? +2. But we've gotten rid of that. So a lot of the machinery that's in your body that like metabolizes sugars can't do it anymore. There's no place for it to react. And so xylitol, we eat it, and then there's nothing that can happen in our bodies, and we just pass it. It just goes right through us, which is great for sugar-free gum because you don't metabolize it, you don't derive any calories from it. Cool. But there's a problem that there are actually some kind of gut bacteria that like this stuff. And so if you eat like a lot of xylitol and you're predisposed to this, you can actually end up with kind of non-healthy bacterial colonies in your gut. I'll also say that if for whatever reason, and you could never do this with gum, if you eat too much of this stuff, it actually acts like a laxative. So, you know, be wise with how much reduced sugar you eat. So this was kind of give you a sense for what kinds of structures we might care about that are related to carbohydrates. In the last section of this video, we'll look at linkages of individual carbohydrate units to make what we call polysaccharides. In this last section of our video, what we'll be looking at is what happens when two sugars react with each other to form more complex chains or linkages of carbohydrates. We typically describe these chains, if there's just two of these individual carbohydrate units, as a disaccharide, so di for two. But these chains can become quite long. They can have 10, 20, 30, 40 sugars attached in a variety of different arrangements, and so we call those structures polysaccharides. You can imagine using other nomenclature as well. A trisaccharide, for instance. I'm sure you can figure out what that might mean. So obviously these structures are very hard to draw, and my board is very small, so we're going to look primarily at the formation of disaccharides. And the reason I think we can get away with that is that the formation of polysaccharides happens in the same manner as the formation of a disaccharide, so the chain just gets longer. So to get started, we'll notice that usually these reactions happen under acidic conditions. So I don't know whether this is catalytic or not, but we know that there's going to be some form of acid. There's also, and this is actually pretty typical, an enzyme involved, right? So an enzyme will help to take these two pieces and bring them close together right where they need to be. And this enzyme usually involves some kind of an acid in its active site. So even though we wouldn't necessarily be adding HCl, this enzyme is going to be using the same kind of mechanisms that, you know, Neanderthal organic chemists do. So we know from previous section of this video that the presence of acid tells me something about roles. I know that there is going to be an electrophilic anomeric position. I've got two different anomeric positions. For the purposes of this particular example, we're going to choose this anomeric position to be our electrophile. This is an arbitrary choice. So we've got our electrophilic anomeric position, and now we need to find in this other structure a nucleophilic site. So we've got a problem. I count at least 5 nucleophilic sites here. 1, 2, 3, 4, 5, and then even potentially the ether oxygen. So anything could, in principle, act like a nucleophile. Now I would maybe think about, well, which of these alcohols is the most nucleophilic? And so if I look at them, they're all going to have about the same amount of electron density. So that's not going to help me. And with the exception of the alcohol on C6, they all have about the same steric profile. So they all have about the same amount of steric hindrance. So what I'm thinking is that the alcohol at C1, 2, 3, and 4, these are all just about as nucleophilic as each other, and I'm not going to have good selectivity. The alcohol at C6 is going to be a little bit more nucleophilic because even though it's got about the same amount of electron density, this alcohol is less sterically hindered, and so it can react a little bit more quickly with an electrophilic site. So if we were going to do this with acid, like from a bottle, like a couple of drops of sulfuric acid, we would have no control really. And you'd have a mixture of products that form where each of these alcohols could act like a nucleophile. An enzyme could actually basically specify which of these alcohols will act as a nucleophile, which is cool. this is one of the things that enzymes are really good at, is they'll basically hold these two structures exactly in place so that only one of these alcohols can really get at the electrophilic site. If you want to think about it, you've maybe got like a little brother or a sister, and if you're at home right now, you could even act this out. It's like if you're holding them back like this, and they're on the other side, and like swinging at you and swinging at you, that's what the enzyme is doing. It's like holding all these other alcohols away so that only one of them can actually engage with the electrophilic center. So again, for the purposes of this video, we don't necessarily know which alcohol is going to act like a nucleophile. I'm going to arbitrarily choose to use the alcohol at C4. Okay, so again, arbitrary choice. I'm just going to choose to make that particular disaccharide. Others could also form. So I know that this is going to be some kind of an anomeric substitution because of the acid and because of the OH group that's present on the anomeric position. And that means that if I choose my C4 alcohol to be our nucleophilic site, that this alcohol will end up bonded to this carbon. So this is the bond I'm making. And that means I'm going to lose this OH group entirely and also this hydrogen, so I'm going to lose water. So the structure that I'll end up with is going to take me just a minute to draw here. Most of these alcohol groups will remain unchanged. 2 sections ago we looked at this in this video. And the stereochemistry of this carbon will also not change. This CO bond is not breaking, right? And so now I have to decide which anomer am I going to make. Because I do have the possibility, I am breaking this CO bond, so I could make my new forming CO bond like this. You'll have to forgive the bond angles. Everything else will stay the same on the nucleophile. Or I could make the same bond, but I could make this CO bond axial down. So I'll draw that product also. So these two products turn out to be anomers of each other. Basically, even though I've got this massive unit that's attached to my anomeric position, the only way that these two structures differ is their configuration at this anomeric position, which I'm going to star. So one thing I want to point out here is that the anomeric position that I starred from the carbon that we assigned electrophilicity to and the oxygen nucleophile has a special name because this is the linkage, this bond that we made between one carbohydrate unit and the other. We call this the glycosidic linkage. So this bond right there, that's the glycosidic linkage. Sometimes it's called the glycosidic bond, but the concept is exactly the same. It's the bond that we made via anomeric substitution to bring two carbohydrates together into a single molecule. So just to make sure that you can spot these linkages, which turn out to be quite important since they're attached to the magic center, I'm going to ask for you to find the glycosidic linkage in this structure here, in the anomer of the product. So go ahead and pause your video. Where is the glycosidic linkage in this structure? So you've had the chance to analyze this compound, and again, when we're looking for glycosidic linkages, what we're looking for is the point of connection between what we would identify as two carbohydrate units. So for me, I look for anomeric centers. I look for places that have carbon at a +2 oxidation level. So that's one of my sugars is here. The next anomeric center is way over here. So probably this pyran is one unit, this pyran is the other. And that means that one of those two CO bonds, either the one that's vertical down or horizontal like this, one of those two bonds is the glycosidic linkage. But remember that it's specifically the bond that formed in this kind of anomeric substitution, so it has to be the bond between a nucleophilic atom like an oxygen and an electrophilic atom like the anomeric carbon. So it would specifically be this vertical bond. That would be the glycosidic linkage. So really what we're talking about in these two anomers is essentially the nature or the orientation in space of these carbohydrate units as that glycosidic bond formed. So we also have some shorthand language to describe the glycosidic linkage that we can use here. So this is sometimes going to be called, for instance, the beta 1,4 glycosidic linkage. And the language tells me a few things. The beta tells me about the configuration of the anomeric position. So this is which anomer from our anomeric substitution. So that specifically means that I need to be worried about the anomeric carbon that is a part of the glycosidic linkage. I will ignore, for this language, the other anomeric position that's present in the molecule. The 1 and the 4 tell me about the linkage between the carbon count for one pyran and the carbon count of the other. So we know that carbon 1 is the anomeric position. So carbon 1, and then this other number will be the carbon number that's linked to through an ether to the carbohydrate on the left. So basically this structure here, or this carbohydrate unit, we're going to try to figure out which carbon is attached to this oxygen, the one that's actually making the glycosidic linkage. So we could say anomeric position will be 1, 2, 3, 4. So that number corresponds to essentially the carbon on which the nucleophilic alcohol was attached, or is attached, I suppose. Okay, so we could look at this structure here, and we know that that glycosidic linkage is very similar. I'm using the same nucleophile, so I still know that this is a 1,4 linkage, but now this configuration, this anomeric position, this CO bond at the anomeric position of this carbon is pointed down, whereas the group out here is pointed up. These are trans, and that corresponds to the alpha configuration. So this would be an alpha 1,4 glycosidic linkage. And so the last thing that I want to point out is what would happen if a third sugar unit came in. So one possibility is that we could protonate this oxygen. That would make this carbon electrophilic, and we could actually make a different disaccharide. That's possible. The other thing that can happen, and this is especially true when enzymes are involved, is that this 2 carbohydrate unit will get appended at the remaining anomeric position that still has an OH group. And so we could think about growing our chain of sugars by doing another anomeric substitution here. That would add a third carbohydrate unit with an OH group at its anomeric position, and then you could actually keep going so that these chains get longer and longer and longer. So at the very beginning of this video series for SL08, I mentioned that one of the emerging areas, and especially kind of like a hardcore molecular structural biochemistry, we're starting to realize that the exact nature of these sugars, so both the sugars we're using, glucose versus mannose versus ribose, whatever, as well as the types of glycosidic linkages that we make, are going to dictate specific three-dimensional structures for these kind of very large biochemical molecules, if we have 30 or 40 carbohydrate units, for instance. And those act a little bit like, in a way, kind of like a lock and key. Like there might be a complementary sugar set, or maybe a protein that recognizes that specific shape of OH groups assembled in space and acts as a recognition element. Right? So this is one of the emerging areas that I think humans are going to be very interested in, because it might offer new opportunities to treat diseases in ways that are fundamentally different from what we've done before. Not to mention it's a way for us to understand much better how molecular recognition happens in biochemical situations. So this concludes the video series for SL08. You're now prepared to complete your homework. Have a fantastic Easter weekend.